Alright, hello everyone. Welcome to another AP Chemistry video. Today we are continuing Unit 3 of Properties of Substances and Mixtures. And today's topics, we will be covering the uniqueness of electromagnetic spectroscopy and the properties of photons. Okay, this is kind of a tangent to what we've been learning about because we started off with solids and liquids, solids, gases, and liquids. And now we're kind of going further deeper into a molecule and how it responds to certain forms of energy. So the topic objectives today is to understand that there are certain portions of the electromagnetic spectrum that affect molecular behavior. Okay, and then photons can influence transitions of an atom or a molecule. Now, we've already mentioned spectroscopy back in Unit 1 when we were learning about mass spectroscopy, okay? And it's simply the study of how matter interacts with the electromagnetic spectrum, okay? And there are certain areas in chemistry where you focus on one particular portion, okay? If you don't remember, if you didn't know, there are basically 7 areas of the electromagnetic spectrum, okay? And even though this visual shows all 7 somewhat equal, some are bigger than others along the electromagnetic spectrum. Okay? For example, the visible spectrum is a very, very small portion of what we can actually detect with our eyes. Okay? But there's also ultraviolet, infrared, and microwaves. And those are the ones that we're going to be focusing on today. Okay? And how they affect molecules. Okay? So microwaves, okay, change the transition in rotational levels around any axis of a molecule. Okay? Meaning, when a molecule absorbs microwave radiation, okay, it's going to make that molecule start spinning around an axis. Okay? So if we look at carbon dioxide, all right, around a three-dimensional XYZ plane, okay, if this molecule were to absorb energy, okay, it would start spinning around this axis, okay, like this. Okay? Alternatively, it could also spin around this axis. Okay? So it's this rotational movement of a molecule when exposed to microwave radiation. There's also infrared. Okay? Infra meaning below, and the red visible spectrum. Okay? This affects the vibrational levels, or the vibrational energies of a molecule. Okay? And a very common analogy to explain this is to consider or to think of covalent bonds as if they were springs. Okay, kind of like a slinky. Okay, and when a molecule with any covalent bond, whether that be a single, double, or triple, okay, there's some movements that you're going to see within this type of energy vibration. Okay, there's what you call bending, where the middle atom of a molecule kind of goes back and forth, and that's hence why they call it bending. There's symmetric stretching, where the bonds opposite of each other on the central atom kind of go back and forth at the same time in the same magnitude. And if there's symmetric stretching, there's also asymmetric stretching, where kind of like the middle one, the same type of stretching occurs, but not in the same magnitude. Okay, and this is kind of where you can kind of think of it as the middle atom kind of going back and forth. Okay? So all these types of stretching and bending can occur when a molecule absorbs a certain amount of energy. FYI, apparently asymmetric stretching requires a little bit more energy. Okay? There's also ultraviolet radiation. Okay. Now, if microwave was rotational and infrared was vibrational, ultraviolet changes the electronic levels for the entire molecule. Okay. And you can kind of think of this as an excited state versus a ground state. Okay. So we're still going to be looking at carbon dioxide, but, all right, when it absorbs electronic energy and releases that energy, it's going to go down a certain energy level, okay, from 1 to 0. The ultraviolet electromagnetic radiation, how it affects molecules, is very similar to atomic spectra in the flame test lab that we did in a previous class. Okay, we learned that electrons can absorb energy from a ground state to an excited state. Okay? But when that electron relaxes to go back down to the lower orbital, it releases energy. Okay? And that's kind of the same thing that's happening with a molecule and ultraviolet electromagnetic radiation. So, here's a practice example. Diatomic nitrogen is colorless, but diatomic iodine is purple. Okay? What properties of those three that we learned explain the difference in the color change? All right, moving on to photoelectric effect, okay, which is the relationship between wavelength, frequency, and energy when a photon is absorbed or emitted. Okay? This is kind of getting into the physics of molecules, unfortunately. Okay? But give you some detail, or give you some background information. Back in the late 19th century, people thought they had physics figured out. Okay, and they thought that energy and matter were directly correlated. Okay, and that matter can continuously absorb and release energy at any point in time. However, based on some empirical evidence in the lab, a scientist by the name of Max Planck realized that there were some inconsistencies with their current understanding of physics and what he was seeing in the lab. Okay, because he would have these substances and he would measure the amount of emitted radiation from these substances and notice that they only emitted at certain energies. Okay. So he came up with this idea that energy is quantized, okay, for atoms and molecules, meaning that the atoms that make up those molecules, okay, will vibrate at specific frequencies. Okay. And he came up with this equation. Energy is equal to N times H times V, where E is energy, N is the energy level, H is Planck's constant, representing 6.63 times 10 to the negative 34 joules, and V is the frequency. Okay. So in order to calculate how much energy a substance needs to vibrate or radiate energy, it has to absorb a certain amount of energy first. So here is kind of a visual of what that previous slide was saying. So initially we thought that any matter could absorb any amount of energy at any point in time. Okay. However, Max Planck came around and said, well, no, a tennis ball or any matter can only absorb, okay, certain amounts of energy relative to its position. Okay. And that's why we say the levels of energy for a molecule or matter in general is quantized. Okay. And later on, okay, a couple years later, Albert Einstein came around and decided that he could extend Planck's work in relation to light, based on what he was seeing in the lab. Okay? And he proposed that light is made of photons, okay, that is proportional to the frequency of light. Okay? Because what he noticed in the photoelectric effect is that certain pieces of metal were only emitting electrons when that metal was absorbing certain frequencies of light. So he kind of simplified Planck's equation, where the amount of energy is just equal to H times V. And we can use this, okay, to calculate the wavelength of light and its energy relative to the speed of light, the wavelength of that, and its frequency. Oops. Okay. So calculate the wave. So here's a photoelectron spectrum. Okay, something that we learned back in Unit 1. Okay, where the peaks are relative to the number of electrons, and the x-axis is relative to the binding energy of those electrons in those certain orbitals. Okay? So calculate the wavelength in meters to remove a valence electron. Okay? So in this case, how much energy is required? Sorry, what is the wavelength of light that is required to kick out, all right, that valence electron? This 5.57 times 10 to the negative 17 is actually the energy of that electron. All right, let's look at how molecules are affected by light. So ozone absorbs UV radiation to protect our little planet's surface. Okay. Now when it does, ozone decomposes to form diatomic oxygen and elemental oxygen, or radical oxygen. Okay. Suppose one molecule of ozone absorbs a photon with a frequency of 1.0 times 10 to the 15 per second. Okay. What is the energy of that photon? And in another question, the energy needed to break an oxygen-oxygen single bond, okay, is 387 kilojoules per mole. Does a photon with a frequency of 1.0 times 10 to the 15 per second have enough energy to break that bond? We will go over these questions in class when we meet again. All right. Thank you for your attention. I know that's a weird, inconsistent lesson based on what we've been learning so far, but that's the AP College Board's idea of an AP Chemistry curriculum. All right. So thank you for your attention. We'll see you in class. Bye-bye.